Alright, so we're going to talk about one more type of circuit, and this one's known as an LC circuit. Because basically what I've got is the L tells me I've got an inductor. The C tells me I've got a capacitor. So an LC circuit is basically I'm going to charge up a capacitor, and I'm going to let a capacitor and an inductor be connected in series. So here you can see is my charged capacitor connected in series with my inductor, and then I've got a switch that I can close the circuit and let the current start to flow. So what happens when I close the switch? Well, initially as the switch is closed, the inductor is going to generate a back EMF, and so at that initial instant there's going to be no current. So notice that initially what I've got is a fully charged capacitor and no current in my circuit. The current will eventually start to build up, discharging the capacitor. So basically we would think of it as current will flow clockwise around this circuit initially as the charge moves off the capacitor. Right? That's where the current comes from, is from the capacitor discharging. That current will increase until it reaches its maximum value, and it'll reach its maximum value precisely at the point where all the charge is off the capacitor. So at the point where there are no charges left on the capacitor, that's when the current is flowing at its maximum value. So the largest value of the current occurs, in this case in the clockwise direction. So the current's going to continue to flow in the clockwise direction, but you'll notice that what that means is now positive charge is going to start to build up on the lower plate. Negative charge is going to start to build up on the upper plate in this diagram here, which means that a couple things are going to occur. One is the current will start to decrease because the charges are starting to build back up on the capacitor, but they're building up with the plate switched. So this is the charge is building back up on the capacitor, but now with the negative plate being up top and the positive plate being down bottom, and that will continue up until the point where the capacitor is fully charged again, and we'll be back to a situation where there's no current. And so you can see that what's going to happen is I'm going to proceed through this cycle, and then I'm going to end up in a situation where I have a fully charged capacitor and no current in my circuit, which basically takes me right back to this initial point where the switch was closed. And so it's going to start the whole process over again, just in the reverse direction. So now the current will start flowing counterclockwise. It'll increase until the point where all the charge is off the capacitor. It'll then start to decrease as the charge builds back up on the capacitor, but it'll flip which plate has which charge. And so basically what will happen is this will just continue to go back and forth. And so it'll just continue to go through this process over and over again. So this is what's known as an oscillatory system. So an LC circuit is an oscillatory system. Basically the current is going to increase, decrease, stop in one direction, then go back the other direction, increase, decrease, stop, increase, decrease, stop, and just go back and forth in an oscillating pattern. Now, of course, we've seen another oscillating system. The spring and mass system was an oscillating system. So we have some sense of what oscillatory systems do. We know that oscillatory systems basically behave like cosine functions. So here I've got the displacement of my mass, right? So when I take my mass, connect it to a spring, pull it away from equilibrium, right, its displacement from equilibrium as a function of time is given by this equation where there's some maximum displacement or the amplitude that you pulled it away from. And then there's this cosine term and this omega t, and here our lowercase omega is what's known as the angular frequency. We can also plot the speed. It's given by this equation, so negative the maximum speed times sine omega t. So you notice that what this means is when the cosine's at its maximum value right here, the sine is at 0. So when the mass is as far away from equilibrium as it's going to get, when it's at its amplitude, the object is stopping to turn around. And then Vmax, right, this maximum speed, we can actually write as the angular frequency times the amplitude. So there's a way to relate the amplitude and the angular frequency to that maximum speed. And so it gives us, so these two equations for the displacement from equilibrium and the speed and the velocity of our mass as it bounces back and forth gives us these two graphs. And so again, we're going to release our mass from maximum displacement, so release it from amplitude at t equals 0, which means its speed will initially be 0. It'll move back towards equilibrium until when it gets to equilibrium, that's when it's moving its fastest. It'll then start to slow down until it gets to the other amplitude, right? So this is the positive amplitude, this is the negative amplitude. Again, at that point, it's going to stop. Now it's going to start to move in the positive direction. So move from negative amplitude back towards equilibrium in the positive direction. Again, when it gets to equilibrium, it's going to be moving its fastest. We'll go back to where it started, and it's going to stop and turn around. So again, here's our oscillatory system all the way through one cycle, and going through one cycle in time means that you've gone all the way through the period. So relating the angular frequency in period for our spring and mass system was given by these sets of equations. So we said we can calculate the angular frequency for the spring and mass as the square root of spring constant k divided by the mass that you've attached to the end. And the period relates to the angular frequency by this equation. It's always equal to 2 pi over the angular frequency. And so in this case, when I take 2 pi and divide it by this, well, my fraction flips over, and so I've got 2 pi times the square root of m over k. So this basically gave me everything that I needed to know in terms of the behavior of my spring and mass system. Well, there's a simple analogy between spring and mass system that we know about, right, that we learned in 221 and the LC circuit that we're going to deal with now in 222. And so basically what it is we can think of, right, you pull the spring out, or you pull the mass out to amplitude and let it go. That's the situation where I close my switch with a fully charged capacitor and no current. Okay? So I let the mass go, and it's going to move back. When it gets to equilibrium, it will be moving its fastest. Well, the current will build up, and again, in this case, the current, given the fact that I started with a positively charged plate on top, negatively charged plate on bottom, that current will flow clockwise in the way this direction is set, or in the way this diagram is set up, and it will reach a maximum value for the current when there's no charge left on the capacitor. The current will continue to flow in the clockwise direction, but now it will build up charge on the capacitor until the capacitor is fully charged again. That's just like the situation where the mass has gone all the way through and is now at the other amplitude. So I have my mass isn't moving, right? I'm back to a situation where the speed of the mass is 0, but it's gone from the right amplitude on the right to the amplitude on the left. Well, there's no current in my circuit again, but what's switched is the polarity of my plates. Instead of it being positive plate on top, negative plate on bottom, it's now negative plate on top, positive plate on bottom. And again, you can see that what this gets me is halfway through the period. Well, now the whole process is going to start over, but with the current flowing counterclockwise, it will reach its maximum value when there's no charge left on the plates. Again, the mass will move back towards equilibrium, and it will be moving at its maximum speed when it gets back to equilibrium. So these are analogous again, and I've come an additional quarter way through the period, so this is now 3/4 of the way through a full period. And then the last fourth gets me back to where I started. So for my spring and mass, I'm back out to mass is at rest at amplitude, at the amplitude I initially released it from. For my LC circuit, the capacitor is fully charged again. There's no current in the circuit, and now the plates are back in terms of the charges being arranged the way that they were initially. Positive charge on top, negative charge on bottom. So this sort of shows you that in the way that we think of a mass bouncing back and forth on a spring, we get exactly the same sort of behavior with our LC circuit. So what we're going to do then is we're basically going to say that the displacement from equilibrium, that becomes the charge on the plates. And all we're going to do is we're just going to use a lowercase q for the charge and a lowercase I for the current, because these are changing values rather than constant values. So here is so our displacement becomes the charge on the plates. The velocity of the mass becomes the current. The mass itself, that's going to be the inductor, and then the spring constant becomes 1 over the capacitance. So basically everything that we've dealt with for our spring and mass system is going to remain exactly the same. All we're going to do is just swap out charge for displacement, current for velocity, inductance for mass, 1 over capacitance for the spring constant. And so what that gets us then is this set of equations that describe an LC circuit. So you notice instead of x is equal to x max cosine omega t, now we've got q, right, the charge on our plates, as a function of time, is going to be equal to the maximum charge on the plate times cosine omega t. The current, there's our negative sign, there's a sine omega t function, there's the maximum current, and again the current, its maximum value can be related to the maximum charge on the plate by the maximum current is equal to the angular frequency times the maximum charge. So the behavior of the charge on the plates looks just like my displacement curve for the spring and mass, and the behavior of the current in the circuit just looks like my velocity curve for the spring and mass. Again, I can relate the angular frequency in the period. The angular frequency is given by the square root of, well, instead of k over m, k was 1 over c, divided by m, that was L. So the angular frequency for my LC circuit is 1 over LC. So I multiply the inductance times the capacitance, 1 over that value, take the square root, that's going to give me the angular frequency. So in radians per second, what's the rate at which my sine and cosine curves are oscillating? And then the period, again, that's still 2 pi over omega, 2 pi over the angular frequency. So in this case, that's going to be 2 pi times the square root of that product LC again. So our LC circuits, here are the equations, and they work exactly the same way in describing what's going on in the LC circuit as a function of time, as our equations did for the spring and mass as a function of time that we learned in 221. Well, the other thing that we kept track of for the spring and mass in 221 was the energy. And so we said that in a spring and mass system, the total energy is just the potential energy, right, the elastic potential energy of the spring plus the kinetic energy of the mass. And so we said that's 1/2 kx squared plus 1/2 mv squared. And so your U potential energy curve looks like this. Its maximum value is 1/2 k times the amplitude squared. Your kinetic energy curve looks like this. So again, when we released the mass, there was no kinetic energy. It was all potential energy. The maximum kinetic energy is going to be 1/2 m times the maximum speed squared. And again, there were a couple special cases here. One was, well, when the mass was at amplitude, so we knew that its speed was 0, which means its kinetic energy was 0, so the total energy was just equal to 1/2 k times the amplitude squared. When the mass was at equilibrium, the opposite was true. So at equilibrium, the elastic potential energy is 0. That's this point. Right? That's when it's gone 1/4 of the way, 3/4 of the way through the period. And so now all the energy is in kinetic energy. And so the total energy stays at exactly this value. And so that tells you that the maximum kinetic energy has got to be equal to the maximum potential energy, and both of those are equal to the total energy within the system at any point in time. So no matter where it is, pick any time you want, whatever location you want, and you can always figure out the energy because it's basically set by how far you pull the mass out and then let it go. Well, we're going to do exactly the same sort of conversion to talk about our LC circuit. So the kinetic energy, we're going to replace that with magnetic potential energy. The elastic potential energy is going to be replaced by electric potential energy. So instead of going back and forth between kinetic and elastic potential energy, we're going to go back and forth between electric and magnetic potential energy with our LC circuit. So for our LC circuit, here's how we calculate it. So again, the total energy is just however much energy is stored in the capacitor, right? So the electric potential energy is the energy stored within the capacitor. One way to calculate that we've seen before, right? We just wrote that as 1/2 Q squared over C. So this is just sort of emphasizing the 1 over C, the 1 over the capacitance here, right? But this is one of the ways that we calculated the energy stored within a capacitor, depending on the charge on the capacitor and the capacitance. Well, we calculate the energy within a magnetic field stored within the magnetic field of the inductor in a very similar fashion, right? That's 1/2 the inductance of the inductor L times the current through the inductor. So this gives us a way to calculate the magnetic potential energy, how much energy is stored in the magnetic field of the inductor. This gives us a way to calculate how much energy is stored within the electric field in the capacitor. And this again is fixed. So basically you start by charging up the capacitor to some maximum value and the current is initially 0. So when the capacitor is fully charged, there is no energy stored within the magnetic field. It's all within the electric field on the capacitor. So the total energy is basically fixed at 1/2 times 1 over C times the maximum charge on the capacitor squared. So this is what the energy is going to be at any point in time. Now, at the moment that the capacitor is uncharged, well, now there's no electric potential energy on the capacitor. And so this tells us that all the energy is now in the magnetic field, and so the total energy has got to be equal to 1/2 L, the inductance, times the maximum current flowing through the circuit square. But either of these values, right, they have to equal each other, because it's just another way of saying the total energy in the circuit, and they have to equal the total energy in the circuit at any point in time. So at some point where there is some current and some charge, so some current in the circuit and some charge on the capacitor, the total energy still has to equal either of these values. And so this is really just conservation of energy, the same way we had conservation of energy with our spring and mass. And so these are the two basic things that we'll deal with LC circuits, is what's going on as a function of time, and then what's going on with the energy through conservation of energy. So our last little sort of diagram here is again just sort of showing us what's happening with the energy. And so here's where we start. So we start with all the energy stored in the capacitor. Right? It's all electrical potential energy, 0 magnetic potential energy. And then as we close the switch and the current starts to flow, well, as the current starts to flow, there is now a magnetic field in the inductor. So we have some magnetic potential energy. There's still some charge on the capacitor, so we still have some left some energy left in the electric potential energy on the capacitor. But as the charges continue to flow off the capacitor, at some point the capacitor is completely uncharged, which means now all the energy is in the magnetic field. So we have the maximum current flowing through our inductor, which means we have the largest magnetic field that we're going to have, and we have the greatest, and so all the energy in the system is now stored in the magnetic field. that current continues to flow and starts building charges back up on the capacitor, so we get some electric potential energy back. That also diminishes the current, so we have less magnetic potential energy, but both of these things still have to add up to what the total electric potential energy here was when there was no charge on the capacitor, which is equal to what the total electrical potential energy was when the capacitor was fully charged. So here it's all in electrical potential energy, here it's all in magnetic potential energy. At either of these 2 points, there's some energy in either. Here it's back to fully charged capacitor. I've reversed the polarity, so I'm only halfway through my cycle, but all the energy is back to being stored in the capacitor. And then all this does is just repeat. So split between the two, all stored in the magnetic field, split between the two, all back to electric potential energy because I now have a fully charged capacitor and no current. So this again is just sort of a nice schematic showing us what's going on with the energy